Hello, and welcome to Dark Souls 2. In this video, I'd like to take a look at these rock textures on this wall and talk about how this texture effect is accomplished. So what we can see if I look at this wall from various different angles, we see that some of these bricks appear to be sticking out of the wall. And this is a really great effect while you're running past a wall, not looking too closely, but it really looks like each of these individual bricks is an individual 3D model. We see some of the bricks are sticking out more than others. Some are more square, some are pointier. We really get a sense of 3D-ness from this wall. But here's the thing. This wall is not 3D in the slightest. And we can see this most clearly here, where we have a corner. On both sides of this corner, we have that same 3D effect. But if we look at the wall from a very steep angle, if we look at the wall flat on, we see that the wall is perfectly flat. That there's no geometry that's sticking out of the wall and no geometry that's sticking into the wall. And we see that as well when we look at the wall from this direction. We see that the wall is in fact a perfectly flat 2D object. So instead of having a really complicated geometry that consists of lots of vertices, lots of edges, lots of triangles being put together to create this highly detailed 3D geometry shape, something else is going on. And this wall is in fact just a very large rectangle that's been cut into two. Everything in 3D graphics is based around triangles, so this very large rectangle has been cut into two triangles, and that's literally all of the geometry that we're looking at right now. There's some other effect that's giving this wall its 3D quality. And I like to call these sorts of effects holographic effects. That is, that we have some sort of flat surface, but the way that the surface looks changes depending on the angle that we're looking at the surface from. And because of that, we get a much clearer 3D effect coming out of this wall. And we can compare that with something like this floor here. This floor is just a perfectly flat texture. There might be some lighting stuff going on. It's hard to tell exactly. But this floor is a perfectly flat texture. There's no holographic anything going on here. We can also actually in this hallway here, this wall does not have a 3D effect. It's the same texture, but the 3D effect has been turned off. I assume for resources reasons, there's a really resource-intensive reflection going on very nearby. And when you're playing this game normally, you're probably running through this hallway to get to the boss fight. So you probably won't notice if the 3D effects are turned off for this hallway. But this is what the wall looks like when we don't have this 3D holographic effect being applied. Now, there are still some 3D-like effects being applied to this wall. The lighting of the wall, your character in this game gives off a light glow, I have extra glowy effects because of some of my equipment, but your character gives off a small lighting glow, and we can see that lighting being reflected off of the surfaces in a very 3D way. This is called normal maps, and this is not what the video is about. This video is not about creating fake 3D effects using how lighting behaves, but rather this 3D holographic effect where it really looks like the bricks are sticking out of the wall, which we don't see here, but which we do see here, or here. In 3D graphics, a scene is built up out of a whole bunch of triangles. And in order to draw this on the screen, the computer goes through a process. First, it figures out where those triangles fall on the screen. Then it figures out which triangles overlap which other triangles so that it only draws the triangle closest to the camera. And then finally, it draws it goes through each of those triangles, goes through each pixel in each of those triangles, and tries to figure out what color to color that pixel. And that final step is based off of the texture image. There's an image file that's being placed onto the geometry. And what we see here is a brick wall. I've kind of exaggerated it a little bit, built up out of a whole bunch of triangles. There are 1,800 triangles here in this particular model. And we see that actually it could probably use a few more triangles. Some of this geometry looks a little bit rounded, and we could improve that by adding more triangles to this geometry. But if this is a brick wall that's like incidental to a scene, we don't want to be wasting so many triangles on putting that brick wall together and making it look realistic. We actually would like to use as few triangles as possible. So our other alternative is to build up our scene out of one big rectangle, two separate triangles, and then be clever when we come to the step where we're trying to color in each pixel. Again, I want to produce some sort of holographic effect where the color of the pixel depends on the angle that we're looking at the surface from. So here I have the code that's used to fill in each individual pixel of triangles once we've projected it onto the screen. So this thing here, this is a basic cube model. It has 12 triangles, two triangles. Each square face is broken up into two triangles, and there's 6 square faces in total. And each of those triangles, right now we can only see the 2 triangles that are facing the camera. Each of those triangles, we calculate what color to color each pixel. And here I have the code that does that. We can ignore norm pass. If we look at UV pass, UV is the coordinate system for describing where we are on these squares. So the starting at the bottom left corner, the U is a variable that describes how far over on the square we are, and the V describes how far up we are on the square. And together, that gives us the UV coordinates. And even if we're looking at the square at an angle, the UV coordinates are still measured on the surface of the square. The computer has done that calculation for you because these are incredibly useful coordinates to have when you're doing calculations. In particular, all we want to do is we have a texture. So this here is the texture that's being passed by the 3D renderer to this piece of code. And all we want to do is say that the color of this particular pixel, these are called fragments in case they don't actually correspond to pixels on your screen, but essentially they're pixels. We say that the pixel color, we should simply look up in the texture that was passed, um, at the location UV pass. So what this function here does is it simply looks up in the texture. It goes to a particular set of coordinates on the texture. You can read whatever coordinates you want, but really the coordinates that this particular pixel, that any particular pixel wants to look up, is its own coordinates. In particular, its own coordinates in the UV coordinate system, right? So if we have a point here, it knows what its u and v coordinates are, and then it looks that up in the texture image that's been passed, and then draws itself as that particular color. And this code gets executed for every single pixel in every single triangle that's visible on the screen. That may seem like a lot, but really there's a lot of graphical effects that require you to do that anyway. And graphics cards are really well designed for that sort of load nowadays. So that's a perfectly fine thing to do. This is very quick code to execute, and we get a surface that has a texture pasted onto it. Now, this surface here is very clearly flat. It is a flat image that we're looking at here. Other than the fact that the texture itself hints at a little bit of 3D, we can see some shadows underneath these bricks. Other than the slight hinting of a 3D effect and our understanding of how bricks work, there's really nothing making this look 3D. So here we can update the shader, the program that determines what color to color each individual pixel, so that the location, here I'm calling it text chord, the texture coordinate, the location that we sample our texture from is getting changed slightly. And we can see what happens with this new shader. If I hit Update Shader, and what it's doing is it's calculating an offset to the texture based on the value of this slider here. So we can slide the slider backwards, and we can slide the slider forward, and that can move the texture forward and backwards. And this is easier to see if I put a frame around everything. And we can see when we move the texture backwards, it looks like we're peering into some sort of window that goes on forever. And if we move the texture forwards, it looks a little bit like it's sticking out of the surface, although this effect is not nearly as good as the effect when it is sticking into the surface. So let's imagine that we're trying to calculate the color that we want to associate to a particular pixel on this surface. So we have access to a vector, which is the direction from the camera to the surface, and we're going to want to continue that vector into the surface until it hits a virtual surface, the kind of inward surface that we're seeing here. We're going to want to virtually trace out this vector so that it continues until it hits this virtual surface, this holographic surface that we're trying to create an image of. And now imagine that we're taking a cross-section through the plane that this view vector is going through. It looks something like this. Here we have our view vector. Here we have our surface. Here we have our virtual surface. And we're trying to figure out what color to color this pixel here on the surface. And in order to do that, we're going to want to figure out the location on the virtual surface that corresponds to this particular light ray. And as we can see, if we set up these similar triangles here, the offset, how far over we need to go from the real surface coordinates to the virtual surface coordinates, the place that we want to sample on the texture, is simply going to be the components of the view vector, the view direction vector, the vector from the camera to the surface. It's going to be the components of that times the highness, the depth from the real surface to the virtual surface, divided by the z component, the component of the view vector that is perpendicular to the surface. And if we do that calculation, that gives us our offset, and we simply take the coordinates that we would have sampled, and then we offset those coordinates. And then finally, if we take the modulus, the remainder of the x and y coordinates of the sampling that we're trying to do, and take their remainders mod 1, the coordinates for our texture go from 0 to 1, so that's simply going to take any sort of coordinates that are outside of the range of 0 to 1 and move them into the range of 0 to 1 with a repeating pattern. And so we can see what happens if I remove this modulus. And that is that points that are directly behind the square that we're looking at, the textures work out perfectly the same, and then points outside of that square, outside of that 0 to 1 and 0 to 1 square that we're looking at, instead of getting wrapped around back into the 0 to 1, 0 to 1 square, we're actually sampling points outside of the domain of this texture. And so what happens by default, graphics programs really don't want to crash, so they simply pick the points that are closest on the texture to the value that's being sampled. And so we see here, we see these gray values, and these red values here are simply the values that are closest to those points that are being sampled. So not as exciting of an effect. If we put the modulus back in, it starts wrapping around, which is what we want. But of course, our brick texture is not a simple inward or outward texture. The brick texture is lumpy. And so what we want to do is we want to modulate this effect here by how deep the texture is at a particular point. We can imagine some sort of lumpy surface here when we take the cross section through the plane that the view vector passes through. And we're interested, really what we're interested in is figuring out the first point where, when we trace this view vector out, it hits the surface. Unfortunately, that's actually a really tricky thing to do. What we can do instead is sample the height of the surface at the point where we hit the surface, which is probably going to be close. It won't be perfect, but it'll be okay. And use that to modulate this kind of depth effect that we're looking at here. So here, instead of setting the depth to be based on the value of the slider, here I'm setting the depth to be some multiple. We're sampling a different texture. We're sampling, in this case, we're sampling the height texture, right? So the height texture, let's actually go back to this. And so the height texture looks like this. It's black where the surface is as deep as possible, and it's white where the surface is as far forward as possible, and it's kind of shades of gray in between. So this is a texture. All of the coordinates, the red, green, and blue color values on this surface are all the same. So it's some sort of grayscale shade that we're looking at here. And what we're going to do is we're going to sample that texture, which I'm calling height, and we're going to sample that at the point where we hit the surface, which again isn't quite the point that we're interested in, but it's good enough. and we're going to sample the texture at that point. So when we sample the texture, it gives us a four-dimensional vector, a red, green, blue, and also alpha value. And we just want the first coordinate of that vector. So I'm taking that vector .x, and then I'm modifying it a little bit, but ultimately that's going to describe the depth that we're looking at here for the surface. And then I'm going to use that depth that we've calculated and modify the coordinate that we sample our texture at. So this here is a very basic parallax shader. And if we look around, this surface here, we can see that it has a little bit of a 3D effect to it. It looks like the tops of the bricks, the fronts of the bricks, are moving relative to the mortar that's behind. And I will remind you, this is a purely 2D effect. This is a purely holographic effect. All we're doing is changing the coordinates that we're sampling our surface texture at. And this small change produces a very convincing 3D effect. It's not perfectly convincing. If we look at it too far from the side, it actually looks a little bit like there's a rounded object floating above a backdrop that is further behind. And what's causing this effect is that when we sample a point such as here, this point here is actually, if we look at it face on, it's actually in the mortar. It actually has a depth that's very low. And so this point on the surface is going to appear as if it's really low, because that's the depth value that's being sampled there. On the other hand, if we actually imagined this as a 3D object, we would want the depth that we treated this point as having as being actually quite a bit higher, because it's on the side of a brick. But we don't know that, right? All we're doing is sampling this point here viewed from straight above, and the height value that is showing up there. So this isn't a perfect effect, and you can modulate this effect by working with your art team to come up with a really good texture and a really good height map that will kind of hide these particular artifacts that we see. These artifacts are mostly just caused by sharp jumps in the height value, right? When the height goes from being really, really low to being really, really high, when we see that, or when we have very small peaks, that's when we get artifacts. But if we're looking at a surface mostly face on, not from low angles, but mostly face on, and if the surface doesn't have a lot of jumps in height, then this is actually a really effective effect, and it's really cheap and easy to do. These computations are not particularly intensive, and it looks really good, especially if you're not staring too closely at it. We see a few artifacts. We see some smearing. We see some replication of pixels. And these seem to be the same sort of artifacts that we see in Dark Souls 2. So I want you to take a close look at these sections of the screen as I move the camera around. What we see is a little bit of warping. And that's exactly what we see in the version that I've implemented. So I conjecture that the way that graphics works in Dark Souls 2, the way that they're achieving this brick effect, is something similar to, if not the same as, this sort of basic parallax shader. But we can do better than this. Remember that the problem that we're interested in solving is where this diagonal ray first intersects this bumpy surface. And this bumpy surface is being given to us by the depth map, by the texture that we saw that was black and white depending on the height. So we really don't have any mathematical way of solving for the intersection. But we can do a better job of finding the intersection point between this ray and this surface. And the way that we can do that is simply by sampling a bunch of points along this ray until we pass into the surface. So let me show you what that looks like. So here I've divided the surface up into 10 different layers. And what we're going to do is we're going to trace out the view direction vector. We're going to trace out this ray in 10 different steps, going from the top of the surface down to the bottom. So we're going to do a while loop and trace out each of these points, moving along this ray until we wind up below the surface. And that's what this while loop is doing. Current L represents the current height, the current layer that we're in of our ray, and current D represents the depth of the actual surface. And so as long as we're above the surface, continue to update the X and Y coordinates, so we're sampling at a new point, update the depth based on the height map, that texture at that particular point, and then update the layer that we're at, move one layer down. And then we keep doing this until we wind up below the surface. So that point there we're going to use to sample the texture, and that's going to give us the color that we want to draw that particular pixel. So let's take a look at what this looks like. So what we see here are, it looks like a bunch of stacked images that we can put together to make our bricks. And I've deliberately spaced these out quite substantially. We can adjust the slider in order to give them a more reasonable depth. And we see that when the slider is small, we get this really high quality 3D effect. All of the artifacts that we were seeing before are gone. When we look at a surface from the side, it we really see the side of that surface. It's only when we try to get the spacing to be a little bit larger, or we zoom in, or we look at it from an angle, that we see that this effect is made up out of layers. And that kind of makes sense, right? We're only sampling so many points. We're only sampling 10 different points going from the top layer to the bottom layer of our surface. And so really the only information that we're getting about our surface is what the depth map looks like at each of these layers. And so it looks like we've taken a whole bunch of textures and we've just kind of stacked them on top of each other. So one of the things that's really prominent about this effect is when we look at a texture from the side, we can really see these layers. That's because sometimes this ray tracing technique will actually pass through a surface if the ray is only passing through it very briefly. You can imagine a really sharp spike and the ray of light that we're tracing missing it completely because the points that we're sampling miss that particular spike. We also can see another artifact here. On the top of the surface, we see a lot of repetition. And this is simply because the texture of each layer is the same as the texture of the layer before it. And we can fix that by taking a step back. Once we've found a point along our tracing that is on the bottom side of the surface, we can go back to the previous point. We can solve the intersection between two lines and find a more reasonable point to sample. And while this gives us some other artifacts that could be improved by improving our depth map and improving our texture, we see that the repetition is at least mostly gone from this top surface here. This advanced shader does not affect the gaps that we see, the spacing that we see, the layers that we see in the side here, because again, that's caused by rays completely missing. The ray that tries to figure out what color to color this pixel here is completely missing the fact that there's a brick surface between the camera and this point here on this virtual brick. It's missing this brick here that's in the way. And there's really nothing we can do about that other than just sampling more points, or again, we can have some sort of more advanced mathematical algorithm. But as long as the height map is just some random function, there's really not that much that we can do to improve this. But again, this effect is really quite good. And if we reduce the intensity of the effect and we zoom out, it really looks quite good. So one of the things that you might notice here are these stripes up at the top and the bottom, and also a little bit to the left and right, although it's harder to notice those. And that's simply because we're sampling the texture beyond the bounds of the actual image itself. We're sampling X and Y coordinates that are either too large or too small, and the computer's just taking the closest coordinate, the closest values that are actually in the bounds of the texture. But what we can do is we can detect when we've gone out of bounds and discard the pixel. Simply not draw anything there and leave whatever was behind it available. If there's a background or if there's some object behind it, we'll draw that instead of overwriting it. And what we see is that for free, we actually get some really nice looking edges for our surface. So that's a really cool effect. It's a little bit limited. Again, it's not as powerful as if we were to make this out of real three-dimensional geometry that has real three-dimensional geometry effects. Really what we have here is that there's a large square, and we're not drawing some of the pixels in that square. In particular, these pixels here, these pixels here, these pixels here, and so on and so forth. It's a little bit limited, but it gives a really nice effect for relatively cheap. We can see this more advanced parallax mapping effect in Hitman 3 in this texture here. This surface, which has some transparency to it, and I made a previous video about why you see these rounded pixelated corners when you look at these sorts of textures. But what I want you to notice about this texture is that it's a holographic effect. It has 3D qualities to it. We can see, if we look at this from different angles, we can see the full geometry of this particular beam here. And we can also see the artifacts of parallax mapping when we look exactly where we would expect to look to see these artifacts. We can see up close, here we have that same sort of layered effect that we were seeing even in the more advanced version of the parallax shader. And we can see in the background some artifacts that have even more layers to them. It turns out that this effect that's being implemented in Hitman 3 dynamically adjusts the number of layers that are being used depending on the angle that you're viewing the surface at. This is a very common technique because if you're viewing the surface flat on, you actually don't need any layers at all. You just need the one texture. It's really only when you're looking at the surface side on that you need a lot of layers in order to disguise the fact that this image is made up out of layers. And we can see some artifacts here that suggest that this technique isn't perfect, as we saw in the brick wall example that I created. But by being careful about the textures that we choose and the geometry that we choose to apply this effect to, it can be really powerful. This is just an incidental railing within a much larger map, and it has very complex geometry. We could imagine trying to build this design here purely out of triangles, and this would require way more triangles than the budget has for this incidental design here. But because the player isn't going to be staring at it for too long, it's very unlikely that a player is going to notice these artifacts that we were looking at unless they are really staring at the geometry. So this general principle of modifying the function that determines what color to color each pixel on a particular triangle to produce a realistic 3D effect depending on the camera angle, using that information there to modify how the surface looks. This sort of technique is used in all sorts of video games nowadays in all sorts of ways. A lot of building interiors, such as the insides of office buildings in the new Spider-Man video games, are rendered as holograms. There isn't actual 3D geometry in there, it's just being calculated on the fly based on the camera's relative location compared to the pixel that you're trying to determine what color to color it. This effect also shows up in Portal 2 in order to determine how to draw the lights. And I will link to resources about both of those effects down below. So thank you for joining me for this adventure, and I hope to see you in a future video.